Hi all, today we are going to discuss transients during three-phase short circuit of an alternator. So if you take your alternator, because alternator will be like this, so there will be a prime mover, so through the prime mover you rotate the rotor of your alternator. So because of that the three-phase supply will be there, the three-phase supply will be generated and those three terminals will come outside. Or if you want to represent the equivalent circuit of this, the equivalent circuit of this will be in this form. So there will be some EMF generated inside. So that will be in series with the synchronous reactance. So that will come to your terminals. So now whenever these terminals are short circuited, what is going to happen? So actually we are neglecting the value of the resistance. Actually instead of the value of XS, there will be ZS. This ZS is nothing but the resistance R in series with the inductance. So before going for the analysis of an alternator, there are two things. One thing is there is the RL load. So what is the effect of short circuiting of an RL load with a constant voltage? We will analyze that. After that we will see how this generated EMF or the EMF generated is going to affect whenever the short circuit happens in the alternator. So that's why first I am starting with the transient in the RL circuit with the constant AC source. So I am assuming my instantaneous value of the AC source is, this is my instantaneous value. So this value is given by root 2 times of V, because where V is the RMS value, times of sine of omega t plus alpha. So what is the meaning of the alpha? Because we don't know at the instant of closing of the switch whether this instantaneous value is at 0 or it can be at a different value. So depending on that, the actual response of the RL circuit will change. So in order to account for that switching instant, what is the phase of this voltage or how much it is displaced from 0 crossover point, so that is represented by the value alpha. That means the alpha is equal to 90 degrees means the switch is closed when the at the instant my voltage or the source voltage is equal to maximum. If alpha is equal to 0, that means the switch is closed at the instant when my source voltage is equal to 0 value, instantaneous value is 0. So now if you want to analyze the fault conditions, that means when the switch is closer to the short circuit or sudden short circuit happens, how this RL circuit will behave. So that current will contain two components. One component is a steady state component, that means which will remain under steady state conditions, and second one is the transient component. So steady state component we have already seen in basic electrical engineering. We have seen that RL load, when the AC is given to the RL load, how much value of the current will pass. So that is a steady state current. That current will be equal to the V maximum divided by Z sine of, because V maximum is root 2 times of V, Z is the total impedance of this RL circuit, which is R square plus omega L square sine of omega t plus alpha. It is same as the voltage, and here this current will be lagging behind the voltage by some angle because it is RL load. This angle theta will depend on what is the ratio of the XL and the R. So that's why this theta is a tan inverse of omega L by R. Let us take for example, if resistance is equal to 0, then this theta becomes equal to 90 degrees. If inductance is less and resistance is dominating, accordingly this angle will change. I am repeating once again, the current that is passing under the steady state value will be equal to voltage divided by impedance, and this current will be lagging behind the voltage by some angle theta. That theta is equal to tan inverse of omega L by R. This we have already seen in steady state. But now at the instant of closing of the switch, when the switch is suddenly closed, because current cannot change in an inductor, because it doesn't allow the sudden change in current, because initial condition, let us assume it is an unloaded condition, because current is equal to 0, sudden short circuit happened. So current cannot become from 0 to some finite value. That's why at the instant of closing of the switch, this total current will be equal to 0. So I am going to take that constraint for calculating my transient current. So at the instant of closing of the switch, I of 0 will be equal to 0, because it is sum of two components. One is steady state component and transient component, or we can tell that the transient component at the instant of closing of the switch will be minus Is of 0, because we know the steady state component of current is this much, that is root 2 V by Z into sine of omega t plus alpha minus theta. At the instant t is equal to 0, substitute here, this becomes root 2 V by Z into sine of alpha minus theta. But actually the current cannot change, cannot reach to this much magnitude. So that is compensated by the transient current. So the magnitude of the transient current will be equal to minus of this Is of 0, so that the net sum of the current is equal to 0 at the instant of closing of the switch. So the magnitude of transient component of 0 will be root 2 V by Z into sine of theta minus alpha, and this current will decay with respect to time. At what rate it will decay? That depends on the time constant of the circuit, which is given by L by R, the ratio of L and R, or otherwise substituting this time constant here. So your equation for the transient current becomes root 2 V by Z into sine theta minus alpha e to the power of minus R by L into T. Here I want to only briefly discuss you the concept. If you want the complete detail analysis how to calculate these things, so these things will come in transient analysis of the circuits, which will come in basic electrical engineering or network analysis. So this component will decay with respect to the time, or we can tell the total current is the sum of two currents. One is the symmetrical short circuit current and the second component is a DC offset current, because it is not oscillating with respect to time, because there is no time concern, only time constant is here only. It is decaying with respect to time and it is unidirectional, because this one is having both positive and negative waves, but this will have only either positive wave or the negative wave depending on instant of closing of your switch. So this can be represented here. Let us take for example, this is my voltage wave. So this is my voltage wave. So let us assume the switch is closed or short circuit happened at an instant of alpha from the zero crossing. So at this instant the voltage wave is closed. We know the current always will lag the voltage by some angle. That angle depends on the value of XL and R, right? So the current that is passing will be lagging this voltage by some angle, and at the instant of closing of the switch, that magnitude will be equal to root 2 times of V by Z into sine theta minus alpha, substituting in the steady state current. So now this transient current at this instant should be exactly opposite polarity to this one. So that's why this is my waveform for the transient component of the current, and gradually your transient component will die out. So now if you are taking the sum of the steady state current and the transient current at a time t is equal to 0, at the instant of closing of the switch, the net current will be equal to 0. So this is my DC envelope, so gradually decaying with respect to time. So the sum of this DC component plus steady state AC component, the waveform will shift like this. It becomes unsymmetrical, gradually it will decay, and when this DC component completely decays to 0, it will come to the symmetrical wave. That means initially it is unsymmetrical wave because of the DC offset current, and gradually when the DC component decays to 0, it becomes a symmetrical wave. So now you can see here the maximum possible current that can pass during the fault in RL circuit will be this much peak, because this much it can reach, agree with me. So this peak value I can write as maximum momentary current IMM by combining the DC value plus AC value. This is the maximum value. So I am assuming that within this much time, because it elapses this much time to reach this peak, in this time the DC component has not decayed more. That means I can take the DC component at time t is equal to 0 and take the peak value of this current at this point. So if you are taking like this, the maximum momentary current, if the decay of the transient current in the short time is neglected, so this can be written as root 2 times of V by Z sine theta minus alpha. This is my transient component, and this steady state component, because the maximum value is reached there, that's why this will be equal to root 2 times of V by Z. So generally practically the value of R is far less than L. So this theta will be approximately equal to 90 degrees, because this theta is equal to tan inverse of XL by R, because R is negligible. So that's why it becomes 90 degrees. If you substitute here, this becomes IMM will be equal to root 2 V by Z into cos alpha plus root 2 V by Z. So if you are taking the alpha is equal to 0 degrees, at that instant this IMM will be maximum. So that will be equal to 2 times of root 2 V by Z. We know that this root 2 V by Z is nothing but IS maximum, because it is steady state current maximum. So we can tell that under transient conditions or under short circuit conditions, the current can reach up to a maximum value of 2 times the steady state maximum value. So this effect is called as the doubling effect. So as the instant of the fault, also alpha cannot be predicted exactly. So the steady state value is only taken in practice, and this steady state value is multiplied by a factor to account for the DC offset current, because whenever the fault happens, the circuit breaker will not open your circuit immediately. It will take some time. So within the time the DC component will decay. So depending on how much time your circuit breaker is taking, accordingly we multiply with the multiplication factor to account for the DC offset current to the steady state value of the current. So now let us proceed for short circuit of a synchronous machine on no load conditions. So the study of the three-phase short circuit of alternator is almost same as the previous section, but only difference here is the flux linkages are going to affect during the fault. As the flux linkages are changing, automatically this source voltage is a varying magnitude. It is not constant. The terminal voltage of the alternator will go on changing with respect to time. As the three-phase voltages are displaced by 120 degrees, the effect of DC offset is different in different phases. You can see here, let us assume the switch is closed at the instant t is equal to 0 only. So at that condition, voltage in phase 1 will be 0, but voltage in phase 2 is a negative magnitude, voltage in phase 3 is positive magnitude. So accordingly, the current will be lagging behind this voltage by 90 degrees, because practically the loads are purely inductive loads, resistance can be neglected. That means under short circuit condition, synchronous machine can be modeled by pure reactance, right? Even for the transmission line also. So that's why the current will be lagging by 90 degrees. So accordingly, the DC component will be different for different voltages. That's why if you measure the value of the waveform under short circuit condition for different phases, they will have the different type of waveform, because the DC offset will be different for different voltages. Because at the instant of closing of the switch, the instantaneous voltages of different phases are different. That is the reason. That's why in order to avoid the confusion, always we try to analyze the symmetrical current only. So, and that symmetrical current can be multiplied with proper factor to account for the DC offset. So, whenever a three-phase sudden short circuit happens, the current increases to a large value. As R is far less than X, the effect of this current is purely demagnetizing. We have seen in the alternator that under ZPF lag load, the effect is purely demagnetizing. But the air gap flux cannot change instantaneously as per the theorem of constant flux linkages, or otherwise we can tell the magnetic field half Li square, the energy is already stored in the circuit in your alternator. That energy cannot change suddenly. That is the disadvantage of the inductor. So as the energy cannot change suddenly, but your fault current is very high, because of the fault current, what happens? There will be a demagnetization effect and it tries to decrease the field in the air gap. But alternator doesn't allow it. So how to compensate that one? So this demagnetizing effect of this armature reaction or the short circuit current is compensated by the current that is produced in the damper winding as well as field windings, and the flux that is produced by the damper and the field windings at that condition will help the main field flux. So this is what the statement you get in many books. But how they are adding? So how the EMF is induced in the damper and the field winding suddenly? So how can it produce? That will be the doubt all of you will get. So that I am going to explain now. So now we have already seen for the case of RL circuit under short circuit condition, there are two components. So one component is AC component, or this is nothing but steady state component, and the second component is DC component, or this is nothing but the transient component. Agree with me? So now coming to the steady state or AC component, when you are giving to the RYB phases, that current will produce a rotating magnetic field which will rotate at a speed of ns with respect to stator winding. Agree with me? You can refer to three-phase rotating magnetic field. So there I have explained this in detail in synchronous machines. So as relative speed between the stator and the rotor is same, so the relative speed will be equal to 0, because both are rotating at ns with respect to each other. That's why no EMF will be induced in the damper bars or the field winding due to this AC component. But now there is a DC component also. DC component doesn't produce any rotating magnetic field. Agree with me? So now the DC component, when it is passing through this winding, the DC component is stationary, but your rotor is rotating at a speed of ns. That means with respect to this current, because this current produces a flux, with respect to this flux, your rotor is rotating at a speed of ns. So it is nothing but the rotor is rotating at a speed ns and it is cutting the flux produced by the DC component. Because of this, the EMF will be induced in these windings. So that EMF will be induced in such a way it will try to oppose the cause. That means these windings, whatever the EMF is induced in these windings, that means damper bars as well as in the field winding, they will oppose the cause, or they will add the main field flux to compensate for the effect of the fault, And how much time the force will be produced by the damper winding or the field winding will depend on the time constant of the respective windings. So same thing I have repeated here. As a relative speed between the DC component and the rotor is ns, EMF induced in the damper and the field windings, so which decay according to time constant of respective windings. So at the instant of sudden short circuit, what happens? The EMF is induced in both the damper windings as well as the field windings. That means there is a mutual coupling between your armature winding, field winding and the damper winding. That's why at the instant of short circuit, all these windings will act in parallel. That means the total current that is carried will be contributed these three. So these three will act in parallel. So, but the damper winding will have more resistance compared to the reactance, and this ratio of X by R, that means time constant of the damper winding, is very less when compared to the time constant of the field winding. So, within the 1 to 2 cycles, this damper winding will disconnect or it will stop carrying the current. So, after that only field winding will be there. So, at the instant of short circuit, we call it as a subtransient state. After 1-2 cycles, depending on the time constant of XD, these oscillations will die out. So only field winding and the armature winding will be there. So this will also remain for some 3-4 cycles depending on the time constant of your field circuit. So after that, the final steady state value will be the leakage reactance in series with the armature reaction reactance, which is nothing but equal to XS. That means steady state reactance or synchronous reactance. So same thing I have repeated here. At the instant of short circuit, there is mutual coupling between the stator, rotor and the damper windings, so they appear in parallel. So why they are appearing in parallel? This is because of the DC component. Please remember this one. So now the equivalent resistance of the damper winding is more than the field winding. So the time constant of the damper winding, so this is L by R, because resistance is more, is less than the field winding. So after few cycles, the eddy current in the field poles and the damper winding disappears and only field winding will remain. So after few more cycles, the effect of DC component on the field winding will also die down, and finally the steady state will be reached, so where only the armature reaction reactance will be there. So we can tell that under subtransient condition, we represent this by XD double dash, the equivalent reactance, that is equal to XL, that is leakage reactance, plus 3 reactances are connected in parallel. So it will be this one. This is called as subtransient reactance. After some time XD is disconnected, so only XA and XF is there. This is called as a transient reactance. After some more time, we reach the synchronous reactance or the steady state reactance. So from this we can observe that XT double dash is less than, XD dash is less than XD. So the oscillogram output after removing the DC offset, because different phases the behavior is different. So in order to make a general analysis, I am removing the DC offset and only assuming that the DC offset, if it is made 0, how the waveform will come. So that waveform will come like this. Initially, as the reactance is very less, so the current will be very high, and this initially high current will go on decaying with respect to time, and finally it reaches the steady state. So during subtransient condition, the reactance is minimum, so current is maximum. So under transient conditions, so after subtransient period comes the transient period. So during the transient period, the damper winding is not there, only main field winding is there. So because of that, the current is little lesser than the subtransient condition. After some time, that will decay finally and reach the steady state conditions. Or this one I can plot like this. If you are plotting with respect to time, this is my steady state current. So it is extrapolated and extended up to here. Let us assume it is represented by OA. So OA represent my steady state current. So the steady state current I will be equal to OA divided by root 2, because OA indicates the peak value. So this is nothing but EG divided by XD. That means under steady state conditions, the direct axis reactance will be there. So now this is the curve, this is the envelope of the current, how it is decreasing. So if you are extending the transient period envelope, if you are extrapolating, it will intersect at a point B. The difference between this B and C, so this is called as delta I double dash. So this gives the difference of the current between subtransient and the transient conditions. Similarly, the point G, where this transient envelope is intersecting, the difference between this point and your steady state point, so this gives delta I dash. That means it is under the transient conditions. How much is the difference in current between steady state and the transient current? So what is the transient current? Transient current I double dash will be equal to OB divided by root 2, which is nothing but xg divided by xg dash. So the difference between I dash, so this is not I double dash, this is equal to I dash. The difference between I dash and I is nothing but equal to delta I dash. Similarly, I double dash will be equal to OC divided by root 2, which is EG divided by XD double dash. So now what will be the short circuit under the cases of loaded synchronous generator? So to analyze the loaded synchronous generator case, so in order to account for the pre-fault current that is passing to your alternator, so let us assume the alternator is applying some load. The load current is equal to I naught and the load voltage or terminal voltage is V naught under steady state conditions. So under the steady state conditions, the value of EG will be equal to V naught plus I naught multiplied by XD. Agree with me? So now when the sudden short circuit happens, in order to account for this pre-fault current, what we will do, we will not take the EG value as the constant. The EG value will be taken by accounting for the initial value of I naught and V naught. So how it will be accounted? For sub-transient conditions, we will calculate the value of EG double dash will be equal to V naught plus J times of I naught multiplied by XT double dash, because under sub-transient condition XT double dash is there. So this voltage is called voltage behind sub-transient reactance. So this EG double dash is taken in the analysis. So similarly for transient analysis, we will take the value of EG dash will be changed to V naught plus J times of I naught into XT dash, because practically whenever the fault happens, the fault current is so much dominating when compared to the load current. That's why no need to go for this analysis. But wherever you want to consider the effect of the pre-fault current anyway, then you can go for these equations. That means entire analysis, equivalent circuit, all will be like before. Only thing is, instead of taking the E as a constant magnitude, here we take the account for the pre-fault current for calculating the fault analysis. Getting this? I hope that what will happen when a short circuit of a alternator happens is clear to you. So with this I am completing the complete fault analysis of the power systems. I hope everything is clear to you. If you still have any queries, you can leave your comments in the comment section below. I will answer to your queries from there. Thank you very much.